The purpose of this lab is to demonstrate the Fresnel equations using a 3D printed apparatus and smartphone camera. The Fresnel equations describe the reflection and transmission of light when incident on an interface between two different optical media. This behavior was first studied by Fresnel in 1827. When an electromagnetic wave strikes the surface of a dielectric, both reflected and transmitted waves are produced. Polarization with respect to the reflection plane alters the intensity of the reflected and transmitted waves. The two extreme cases, when the wave is perpendicular to the reflection plane or parallel to the reflection plane, are known as S and P polarization. In this lab, we studied S polarization. When an electromagnetic wave is incident on an optical surface, it is partially reflected and partially transmitted. The transmitted wave is propagated with respect to Snell's law, while the reflected wave is propagated with respect to the law of reflection. While there are many things the Fresnel equations can tell you, in this lab we focused on the reflected light from a S-polarized wave, the first equation on this page. The device itself was made up of several 3D printed parts. The base was mounted on a wooden platform with a rotating piece in the middle that suspended a glass slide. The angle of this centerpiece was measured by a protractor, and then the reflected laser could be measured using a swing arm that held the phone camera. The total cost of this project was approximately $13. The picture on the left shows the perspective from the phone camera, while the picture on the right shows the location of two small pieces of polarization material which we used to achieve S polarization on the wave. For the experiment, the laser beam was directed at a glass slide which was reflected directly into the CCD of the phone camera. The angle of the glass slide was changed over a range of 70 degrees to 6 degrees, and the phone camera was moved accordingly. At every 4-degree mark, a picture was taken of the laser beam. For the analysis, each picture had the color strip from it to create a grayscale image. The brightness of each pixel in the image was then added together to create the overall brightness, which was divided by the number of pixels to create the average brightness of the picture. Because the laser beam was the only light source in each picture, the brightness changed with respect to how intense the laser beam was. The graph on the left is a result from our experiment, while the graph on the right is a mathematical representation of the law. The chi-squared value for our graph was 0.302, making it a very good representation of the mathematical law. While the beam exhibited classic S polarization behavior, the result could have been improved by the use of a high-resolution 3D printer, an adjustable shutter and gain of the CCD camera, and perhaps the use of several different reflective media to test it out over a variety of optical surfaces.